We are moving on to section 8.7. This is actually something that I asked you to learn at the very beginning of our closure last March. It was the one topic on the list of AP topics that we hadn't got to. I do realize that was March and it was 6 months ago, so we're going to pretend like that never happened, and I'm just going to kind of teach it as if you've never heard me talk about it before. So either this is going to sound vaguely familiar or it's going to be a first time. So the section is called L'Hôpital's rule. I know it looks like the hospital, but it's actually named after a mathematician who was not surprisingly French. And what L'Hôpital's rule does is it looks at specifically limits and kind of gives you an easier way to evaluate limits that maybe were a little more challenging algebraically, or they weren't algebraic, so they were very difficult to do. So before we get into L'Hôpital's rule, I want to talk about what you already should know about limits, going all the way back to the beginning of Calc 1. You should know when you're looking at a limit that has x approaching any constant. So that's why I'm saying x approaches c. A couple things that we can do with that. We can directly plug that number in. So if you look at this first example, and I'm plugging in 3 into the top, I'm plugging 3 into the bottom, I get 13/8. Keep in mind, this represents a y value. So your answer to a limit equation is, get rid of that, is asking for what y value or what height does it approach. If direct substitution didn't work, then our fallback plan were algebraic options. So we could, my favorite, we could factor and cancel. And once you factor, like this example you're looking at here, and the x minus 3's cancel, you're left with x plus 3. Then you plug in your constant. So then you plug 3 in and you get 6. When you have something like this where you're canceling away the discontinuity, essentially there's a hole there, but my limit still approaches that value even though that hole is empty. Another thing that we did algebraically that I'm not even going to mention because I don't enjoy it is we rationalized denominators when we had square roots. No fun at all. L'Hôpital takes away the necessity of ever having to do that. We also had what's called limit guidelines. We did these in chapter 3. Limit guidelines were how we were evaluating limits as we go to either positive or negative infinity. And the key was we were looking at a rational function and we looked at the degrees. If the degree is bigger on top, so like this one has a bigger degree on top, essentially what's happening is the top's getting bigger faster. It kind of wins and beats the denominator, which means your entire thing gets bigger. So you go to infinity. If the bottom has a bigger degree, then the bottom is the what's getting bigger faster. And if you start dividing by something bigger and bigger and bigger, you're going to get smaller and smaller and smaller and go to 0. And then your last option is that your degrees are exactly the same. And in that case, we can say it's kind of growing at the same rate, and that rate will be the leading coefficient ratio. So if we have 3x squared over 1x squared, we get 3. So those are some limit things that you should already be very comfortable with. So here's what L'Hôpital does. L'Hôpital allows us to deal with with limits that result in what's called an indeterminate form. Indeterminate form means exactly what it sounds like. It is something that we cannot determine. If you go to evaluate a limit and you get 0 on the top and 0 on the bottom, you're basically stuck. I like to think of it as a clashing of rules. 0 divided by anything should be 0, but anything divided by 0 should be undefined, but anything divided by itself should be 1. So you have this clashing of all these algebraic things you've learned since probably pre-algebra. Same with infinity over infinity. On one hand, you'd think, well, it's infinity on top, so it's getting really big, but you also have infinity on the bottom, so it's getting really small. But you have 2 infinities, so when I divide them, should I get 1? So that's what L'Hôpital helps us deal with. If you have one of these forms, it gives you kind of a fallback plan. So here's what his rule actually says. So if you're trying to evaluate a limit that is rational, we're always dealing with rational things here. So we think of it as like f of x is your numerator and g of x is your denominator. And you get a result that is indeterminate. So you get 0 over 0 or you get infinity over infinity. Then what his rule says is, well, you can try to take the derivative of the top. You can take the derivative of the bottom. Notice this is not a quotient rule. This is literally just taking the derivative of the top, the derivative of the bottom. And then you can try again. What I mean by try again is now try to plug the number in. If it's the limit as we go to 5, now put 5 in. Whatever answer you get will be equivalent to what you were trying to find when it was indeterminate form. So it gives you a way, as long as you know how to derive, to find that limit without having to take a lot of extra algebra means. So here's how it looks in action. So this particular one, first, when I put 3 in, just double check that when you put 3 in, you do get 0 on the top and you get 0 on the bottom. So it is an indeterminate form. You want to check that because what if you actually get 0 on the top and 10 on the bottom? Then the answer is 0 and you don't want to do anything that doesn't need to be done. So there was a way to do this by doing rationalizing and multiplying by the conjugate. Again, nothing enjoyable. So the L'Hôpital option is take the derivative of the top. So the derivative of the top is a chain rule, power out front, power 1 less. Derivative of what's inside is just 1. Derivative of the bottom is 1. Now see what happens when I take the limit. I get very lazy writing my limits, and I have been to AP conferences and they say, make sure your students always write the limits over and over again. And I'm like the first to admit I don't do that myself. So now I put 3 in. All I did was just clean this up with this negative exponent. When I put 3 in, I get 1 over 2 times the square root of 4 is 2. So 2 times 2 is 4. And that's my answer. And it would have been the same answer had I got if I would have multiplied by the conjugate and remembered all the algebra from algebra 2. Next one, if I put 4 on the top, so 4 squared, 16 minus 28 plus 12 is 0. 4 squared, 16 minus 12 minus 4 is 0. Now with one like this, I love to factor, so I might just forget L'Hopital and just go into factoring because it's something that I enjoy. But if you don't enjoy it, I don't know what's wrong with you if you don't enjoy it, but if you don't enjoy it, the backup plan is you can take the derivative of the top, which is 2x minus 7, the derivative of the bottom, which is 2x minus 3. Now take the limit as x approaches 4. So when I put 4 into the top, I get 8 minus 7, which is 1. If I put 4 into the bottom, I get 8 minus 3, which is 5. And that's your answer. Where it actually, let me show you one more of those. So when I put 2 on the top here, I get 0. When I put 2 on the bottom, I get 0. If you want to factor instead of do L'Hopital, so you might say, you know what, I love factoring, let's factor. Let me just remind you how that works. So if you want to factor, you can cancel, and then you can put 2 in, and 2 plus 1 is 3. Or if you want to say, forget that, I'm going to do L'Hopital so I don't have to factor anything, I can do that. When I take the limit of the top derivative divided by the bottom derivative, I get 4 minus 1, which is 3. So you get the same answer. It really gives you options when you're dealing with more algebraic type functions. When you're dealing with ones that are not algebraic, so you can't factor them because it's not something that's factorable, because it's something exponential like this one, or when you're looking at something that you can't rationalize, now L'Hopital goes from being a really nice, helpful way to go about it to being a necessity. With this one, when I put 0 in, e to the 0 is 1. So you get 1 minus 1, which is 0 over 0. Now I have no choice but to know L'Hopital. So I take the derivative of the top, 2e to the 2x over 1. Now put 0 in. When I put 0 in, I get 2 times 1, which is 2, over 1. That is one where if you don't understand how L'Hopital works, you couldn't do that one unless you maybe went to a graph and started looking at the graph and see what happens around 0, which wouldn't be super efficient way to do it. So we go from, again, being a convenience to a necessity. You'll see on the AP test, most of the examples they do are more of a necessity ones. They don't want, if they want to test if you know L'Hopital, they don't want to give you one that you can do it a different way. This one, when you take the natural log of infinity, it does go to infinity really slowly. This is what natural log looks like. So it's going to infinity, just really, really slowly. Over infinity, which is another time that you can use L'Hopital. So the derivative of the natural log of x is 1 over x. The derivative of the bottom, x, is 1. So we just get 1 over x. Now when we put infinity in, 1 over something getting really, really big is going to go to 0. Again, this value, this is your y value. So what this is saying is if I were to graph this function, so if I went to my calculator and I graphed that function, and I looked at what happened as we went to infinity, meaning as we go farther and farther to the right, you would see a graph that is flattening out towards 0. So if you're wondering what this answer actually means. Next one. So as x is being cubed, as I go to infinity, that's going to go to infinity. E going to infinity is also going to infinity. They're both getting really big, really fast. So I take the derivative of the top and I take the derivative of the bottom, and I still get something that's going to infinity over infinity. So I do it again. This is called a repeated application of L'Hopital. Essentially, you did the process, you're still getting something indeterminate, so you do it again. Well, you're still getting infinity over infinity, so you're going to repeat it one more time. And the reason I say one more time is you no longer have an infinite value in the numerator. Now you have a 6 in the numerator, and you have something really big in the denominator. That is going to go to 0. One thing that I want to caution you is don't do it more than it needed to. So if you just keep going, I'm on a roll, I'm just going to keep going. If you don't get 0 over 0 or infinity over infinity, you can't do L'Hopital again. So you can actually overuse it if you kind of get going. Another thing you can do with this one is kind of more of like a theoretical idea. If I look at that function, I have a polynomial on top, I have an exponential on the bottom. As I go to infinity, the exponential is going to get bigger faster. Exponentials are way bigger than polynomials over the course of time. So it's probably not shocking that you got a 0 because essentially the bottom won. The bottom got bigger faster. Want to show just last two. These are probably the most common ones I've seen on the AP test. I feel like on the AP test, they tend to do ones that are either very generic, and we'll do some of those in class, or trig or E-based, where they're kind of forcing you to understand this rule. So the sign, when I put 0 in, the sign of 0 is 0. Over 2 times 0 is 0. So I think they like this question because it forces you to remember how to take your trig derivatives. The derivative of sine is cosine, but then you also have to take the derivative of the angle. The derivative of 2x is just 2. Now when I put 0 in, the cosine of 0 is 1, so we get 6 times 1, which is 6 over 2, which is 3. I've also seen them do this with tangent. Tangent is 1, no, this is written wrong. This should be, I wrote it wrong. Change this. This should be to 0. I didn't change my my math formula when I was typing it in. So sorry, this should be 0. Tangent is 1 that you should know the tangent of 0 is 0. Tangent tends to show up a lot with L'Hopital because they always harp upon the tangent of 0 being 0 over 0. The derivative of tangent is secant squared times the derivative of the angle. So you can put the 3 in front or at the end. I think it makes more sense to put it in the front. Over 2. Well, now you have to know the secant of 0. Secant is the reciprocal of cosine. So kind of let me walk you through this. The cosine of 0 is 1. The reciprocal of that, because that's what secant is still 1. 1 over 1, 1 over 1, doesn't matter how you flip it. When I square it, I still get 1. So all of that work, I end up with 1 times the 3 over 2. Those are the basics of L'Hopital. I'll show you some ones that are maybe a little more complicated and worded differently, but I wanted to, at least while you're home, give you a chance to refresh what I maybe had taught you in March that you didn't remember, or maybe it was something that you didn't look at in March, and now you know.